While the k-means algorithm is widely used and has many advantages, it also has many challenges. The broad applicability of the algorithm in many clustering application areas can be attributed to its implementation simplicity and low computational complexity. But some of its drawbacks should be considered. The algorithm, for a start, is extremely sensitive to initial conditions. Another known difficulty is how to select the k parameter. It is also not straightforward to how to handle categorical data, as we have stressed previously. Outliers can impact the results, it assumes round clusters, and it may face challenges with large datasets. The speed of the algorithm for large datasets is also not the best. But let us see each of these limitations and others in more detail. To start, k-means is very sensitive to initial conditions. The algorithm initializes the cluster centroids at the beginning, with the final clustering results varying according to these initial positions. Poor initialization can lead to an increased number of required clustering iterations to reach convergence, and a less efficient algorithm overall. We show here an example based on data shown previously. Remember this dataset from the previous video? We have here 5 clusters. The navy blue and the green clusters are the ones that are harder to distinguish. Imagine that we depart from a situation where we do not know the cluster's real colors, so they are gray. Imagine also that we use random partition initialization. You obtain the initial centroids shown here as black dots. The random partition strategy has a tendency to place the centroids at the center of the data. Indeed, we can see here the centroids at the center. This set of centroids leads to a good clustering, despite its tendency to concentrate the centroids at the center of the data. But what if we had a different data configuration? Imagine that clusters 1 and 2, the navy blue and the brown, were slightly closer to each other. Let us now see what happens when we hide the true colors of the cluster and run k-means on the data. Using the same initialization, random partition, we obtain centered centroids again. From these centroids, using the same k-means algorithm with the same configuration, we obtain very different final clusters. This is surprising but also very undesirable. We would like that initialization would not impact so much the final results of the algorithm. This makes the k-means algorithm less reliable and not so much reproducible. This is in fact one of the major challenges of k-means and of the initialization methods that we devised for the k-means algorithm. But how can we overcome initialization bias? Well, we can use many different strategies, such as running the algorithm multiple times with different initial centroids, or using a smart initialization method such as k-means++. We have a video dedicated to the possible initialization approaches to k-means. Another drawback of the k-means algorithm is that we have to set the number of clusters, the k, in advance. Choosing an incorrect number of clusters can lead to inaccurate results. Going back to our example of 5 clusters, let us see what happens when we set the k to 4. Here we are using an advanced form of initialization with k-means++. It is obvious that the end result is not very satisfactory because we are merging data points into a single cluster that should indeed be separated. Here the problem is the configuration of the number of clusters, setting the k parameter. Imagine that in another possibility that we set the number of clusters to 6. What would happen then? Then the method is able to detect the clusters more correctly, but it forcibly needs to partition one of the clusters into 2. This is not correct, and it is a situation that should be avoided. In a two-dimensional world, it is quite easy to spot the optimal number of clusters by simply visually inspecting the data. That is not the case when we talk about 3 dimensions, and especially for higher dimension spaces. To mitigate this difficulty, various methods are available to estimate the optimal number of clusters, the K, such as the silhouette analysis or elbow method, but they may not always provide a clear-cut answer. Another drawback of the K-means algorithm is its inability to handle categorical data. The algorithm works very well with numerical data, where distance between data points can be calculated. However, categorical data doesn't have a natural notion of distance or similarity. When categorical data is used with the K-means algorithm, it requires converting the categories into numerical values, such as using one-hot encoding. One shortcoming of using one-hot encoding is that it treats each feature independently, and it can degrade performance since it can significantly increase data dimensionality. We have another video dedicated to this important topic that you may want to check. K-means has trouble clustering data when the clusters are of varying sizes and density. K-means works very well for equal-sized Gaussian blobs, such as the ones shown here. However, it suffers as the geometric shapes of clusters deviate from spherical shapes. For example, when the shapes are more elliptical, the algorithm tends not to work so well. See this example. We can visually distinguish very well 3 clusters. But because of the elliptical shape of the clusters, K-means fails to find the real set of clusters. It looks as if the algorithm is trying to find circles instead of ellipses in the data. The same problem happens when some blobs have different sizes. We can see here an example. The brown cluster has the same number of points within the cluster, but they are more spread than in the other clusters. The variance, the dispersion that is larger in the brown middle cluster. The results of K-means clustering in this scenario are not particularly good. Part of the points of the middle cluster go into the edge clusters. The algorithm tries to fit spherical clusters of the same size, which does not help finding the right clusters in the end. Another scenario where K-means can break is when you have clusters of an equal number of points, an equal density. In this case, the clustering results might not be as expected. For example, imagine that you have 3 clusters more or less of the same cluster size. The difference lies in the number of points within each cluster. One cluster has 10 points, another has 100, and the navy blue one has 500 points. Running K-means on these datasets will lead to a bad clustering. The cluster with the least points will become merged with the closest cluster, and the biggest cluster inside is divided into 2. More complex shapes of clusters are even harder for K-means. If we have the classical case of 2 circles, results are far from optimal. The same happens for semicircles. The clustering results are unfortunately all mixed. Unfortunately, there is not much that we can do to prevent these bad results. The reliances on the Euclidean distance dictates that these more complex and non-spherical shapes make k-means work less well. One unique challenge of k-means clustering is its vulnerability to the course of dimensionality. What does this mean? This means that as the number of features or dimensions in our data increases, so does k-means struggle to find meaningful clusters because the concept of distance becomes less informative in high-dimensional spaces. To address this, consider employing techniques like feature selection or dimensionality reduction, such as principal component analysis, to reduce the number of dimensions and improve the effectiveness of k-means. Additionally, it can be worthwhile to spend some time exploring domain-specific knowledge to identify and prioritize relevant features, and that can be a creative way to enhance the performance of k-means in high-dimensional datasets, making it a valuable tool even in complex multidimensional scenarios. Now that we have covered the different challenges of k-means, we thank you for watching. The next video will be about methods to discover the optimal k. See you in the next video.